over z.
Is that the same alpha from chapter 2?
Yeah, it's the strength of the delta function. Yeah. So alpha has to do with the strength of the delta function. Okay, so here's the coolest thing in the world, guys. So, you know, really kind of look through this section more, and if we ever did a solid state physics course, we would do all this in far more detail. All right, but this is the great argument. All right, just check it out. So figure 5.6. What he does is the following. So he's going to plot this. This is figure 5.6. Okay, on page 228, thank you. All right, and it looks like this. So over here, he has something like here's pi, 2 pi, 3 pi, and 4 pi. All right, and it comes down like this. Okay, I'm not going to get it exactly. Okay, so this is f of z. And if you put in numbers, here is +1 and here is -1. So it goes like this. Okay, why does anybody care about the +1 and the -1? Look way over here. So here's my f of z. Right? And f of z, does that get bigger than ± 1?
Yes.
Look over there. Yes. But what about this cosine?
The cosine should be.
The cosine can't get bigger than ± 1. All right? So in other words, what are allowed solutions? Right, it's everywhere. So here's what he does, and he does it a lot better. So here's our solutions, right? These are good solutions. All right, and then
So eventually we'll be all of that.
here's a good solution, and here's a good solution, right? These are good, allowed solutions.
So eventually though, you'll get everything, right?
What do you mean, get everything?
Eventually that's going to go below ±1. It's decaying.
Oh yeah, I think it will decay, yeah. So I think that's an excellent point there. So I think at some point it will go like this.
Yeah, because it is a decaying graph.
Right, so then it goes like this, and then at some point, you know, starting here, it becomes a true continuum, that these are all allowed. All right, so these answers right here are not allowed. And notice what you start to see is that they have a band. This is called a band gap. Band gap. So this is called a band gap. No allowed solutions. All right, so there are literally no solutions there. Remember, we're going back over here. Now let's go back. I erased it. But we had total kappa equals 2 pi n over NA. All right, where n equals 0, 1, 2, 3, so on. And by the way, there's something different. In these solutions, it's ±1. Oh, and it's 0. So these are a little bit different. ±1, ±2, ±3. All right? Which means that, and so over here we have cosine, okay? And we have now kappa, we can replace kappa with 2 pi n over NA. All right, and that has to equal these bands. for n equal plus or minus 0, 1, 2, 3 to infinity.
There's no A. It's kappa A. I mean Ka, so the A would disappear.
Oh, I need the A, right?
Well, no, it would kill the A off. A divided by A is 1.
This is okay, I put it over there.
No, I mean,
No,
Oh, I see what
the
you mean.
cosine, because you put
it's cosine Ka.
cosine Ka. So
Oh,
A's are
okay,
disconnected.
yeah, there we go. All right, now, what does n get to?
And gets to
10
infinity,
to the 23.
which is
And what about little n? N could be
anywhere between 0
0
and
and infinity. So what it means is for each of these bands, you have a huge number of possibilities within each one of those bands. Right? And so these bands that are allowed fill up with states on the order of the order n states for each allowed band. Right? And so if you have n as the order on the order of 10 to the 23, then these things start to look like almost, instead of being discrete states, these things look like continuous energy. So instead of having like the electron in a 1s or a 2s or 3p, now it looks like when you have these periodic potentials, you have that the electron could be anywhere in this band, and anywhere in this band, or anywhere in this band of allowed energies. Right, and those are those are the allowed bands.
depending on the beta is as well.
What's that?
And the number of bands depends on
It depends on beta and all those things, yeah. Okay. So what we've got here is we've got one electron, right, so far. All right, but now let's make that many electrons. So now we're going to do something like this. Now let's turn it on its side like this and say here's one band, and then here's the next band right here.
We have to change the fermions first, or
Okay, so now let's add a whole bunch of electrons, n electrons. Right, and then let's make them fermions so that each one of those states fill up and up and down. So now you can start to see what's going to happen, that depending on your number of electrons, you're going to start filling up these states with electrons. Right? All right, so that's where we're at. All right, now, okay, so that's what we're going to do. We're going to fill up these bands with electrons. All right, now let's say we go and we do a separate calculation and we calculate the E Fermi, the total Fermi energy. All right, and let's say the Fermi energy comes out to be here. Now, can these electrons with that kinetic energy have this energy up into this area?
they're part of
They can't have it,
yeah,
right?
so they can't
And it
go
doesn't
there.
have enough energy to get up in here. So those electrons stay stuck in here,
This goes back to insulators, conductors, and semiconductors.
and that's what's going to happen, yeah. But now say that your E Fermi was instead just right up to here. Your Fermi was right to there. Then what does that mean? That means you've got electrons that actually have enough energy so that they pass this gap and they start to fill this region right here. But when they're in this region right here, look at all the space that they've got to move. That these are essentially the same energy levels. They're so closely spaced together. So like an electron that jumps up in an electron here, you know, pushes over this way, there's an electron, pushes over this way. So they're kind of free, but everybody's stuck together. Nothing's happening, right? But now, if you get an electron up into here, right, and all of a sudden you put a plus over here and a negative over here, this electron goes, oh man, I can just zoom, you know, right over to here. Or go the opposite way. All right, and so this would be called a conduction. So this would be, if you had your Fermi up here, then this would be a conductor. If you had your Fermi right here or below, this would be an insulator. All right, and then a semiconductor is one where, you know, you might have an E Fermi, you know, up to there, right? But then you could do something like maybe dope it a little bit or change the energies a little bit so that you can end up, you know, the E Fermi might look something like this instead of being a step function. So that you actually, by changing, what happens is the Fermi energy depends upon the temperature too. Well, when you start adding temperature, you can imagine it adds to the kinetic energy. So what you can do is you can start giving some of these electrons with the Fermi energy up here, give it a little bit more temperature kinetic energy, and those electrons can move up into the conducting band and be good conductors.
You can do that with electrons when you add the current.
That's the whole thing.
But semiconductors do have a heat limit where they can't.
Yeah. Okay, so that's all I'm going to do on that. And then, you know, I'd like you to go and read the rest of this, but I did the rest of that, the different distributions. We've done that in modern physics. And what we're going to do is we're going to start right away in chapter number 6, which is time-independent perturbation theory. And I'm just going to start us off for 5 minutes, all right?
Question.
Yeah.
For my, Ed put any of this in my paper for the hydrogen atom?
You know, not really, because it's not in a periodic potential data, right?
Yep, so just.
So if you're not in a periodic potential, you'll never get bands.
We got a two-particle system, so just leave it at that for now.
Yeah, I mean, we're just doing hydrogen with one electron, and so it will never see a periodic potential. So very definitely, here's what Griffiths points out. Band gaps, as opposed to energy levels, are the telltale signs of periodic potentials. So where do you see bands? Where do you see periodic potentials? Where do you see periodic potentials?
When there's a group of atoms.
Solids. Okay. All right, so let me give you the flavor of perturbation theory. This is time-independent perturbation theory, okay?
What about the spin? I don't put that in with